Hey everyone, so we just finished talking about all the different types of energy. So I want to go into a little bit more detail of how to actually calculate each one. So right now I'm actually going to talk about how to calculate work. Now, if you recall, one of the definitions for work was that it resulted in change of energy, but it also uh, was defined as essentially the amount that is displaced based off of the force that's being applied. So we can actually use both of those to come up with the definition. Now, before I actually do that, there is something important to note. In order for a force to do work on an object, the force has to be parallel to the direction that it's being displaced. So when we do work on an object, if I am moving the object horizontally, only the force that acts horizontally or has a part that acts horizontally is doing work. If this makes sense, if we kind of go back to the definition of that it results in a change of energy. If I have an object that's being moved horizontally, I need, in order for it to change energy, let's say in the form of kinetic energy, to gain more kinetic energy, I need to apply a force that is at least has a component that's parallel and also pushing horizontally. So that could mean I'm pushing it like this, directly horizontally, or I might be pushing it up at an angle like this. In both these cases, there's at least a part of the force that is contributing to pushing it forward. If I instead had the object being lifted up, then the force that's acting vertically will be the force that's basically contributing to doing the work. So it's important to make sure that we keep this in mind. So the force that ends up acting on the object and the displacement have to be parallel. This leads us into our first equation. So the equation that you'll see on the reference table is this. Delta E equals W equals F parallel D equals FT cosine theta. So this is essentially saying that the change in the energy that an object gets is equal to the work applied to it. It's equal to the component of the force that's parallel to displacement, which could also be FD cosine theta. Now, I have to kind of explain this a little bit. First, this F parallel is not the same F parallel as the inclined plane F parallel. So we're not doing like FG sine theta for this. This is a different F parallel. This is explicitly saying the force that's acting parallel to the displacement. So if the displacement is acting horizontally, this is basically referring to a horizontal force. If the displacement is acting vertically, then this is referring to a vertical force. That's all that's referring to. Now, going back here, instead of doing FD, I could do FD cosine theta. So here, the key part is this theta. This theta is actually defined strictly as the angle between the force and the displacement. So in this case, the angle, since the force is acting like this and the displacement is horizontally, then the angle is to the horizontal, so that the displacement and is in that horizontal direction. If Now this diagram might not make a whole lot of sense, but let's say the object was displaced vertically and the force was still acting like this. Since this is a vertical distance, vertical displacement, then the component of the force, the angle that I need to actually look at is this one. So if this was 30 degrees, then when I do ft cosine theta, I wouldn't use 30, I would use this uh, so that it's the angle between the displacement, which is vertical, and the force. So I would end up using 60 degrees. Now this leads us into basically two choices when we do work. We can either find the components of the forces, so make all the forces into parts that are either going perpendicular, parallel to the displacement, either in the vertical direction or the horizontal direction, and then choose the specific force that's acting in the direction of displacement or parallel to displacement. If so, I can use this equation, or I can leave everything in their normal forms, so leaving the force at any sort of angle, but then use FD cosine theta where I have to make sure that the theta is between the force and the displacement. The choice is really up to you. I recommend that you kind of try a little bit of both, see what comes a little bit easier for you, which one is less likely to make you mistakes. Personally, I would actually go the route of finding the components first and then just doing FD without worrying about the theta. The reason I would recommend doing that is because in any question where they don't end with just finding one work, but maybe the work done by this force, the work done by this force, the work done by that force, you might have to break it up into components anyway to figure out what the other forces are. For example, if you have an object on an inclined plane, you might have to break up the FG into the F parallel and F perpendicular components in order to figure out what the frictional force is. So it might be useful just to break it up first and then just do the easy case of doing force times displacement. You can do this, but like I said, the theta can get a little tricky in them. So, be careful. Do whatever kind of works best for you. I think that's about it. Yeah. Really quickly. So, one nice question that you could think to yourself is, if a man lifts a box and carries it to his desk, does he do work? And if so, when? So let's take the scenario where the person takes an object from the top of one desk, lifts it vertically up to some distance, moves it horizontally, and then places it down. There are 2 points in this scenario. Let's say section 1, section 2, section 3. There are 2 points where where the person's doing work. In section 1, it ends up doing positive work, and section 3, where it actually does negative work. In the section 2, it actually does 0 work. Now here's another interesting thing. Since the object is being lifted up and placed down, even though it doesn't explicitly say it, we're going to say that we're using the same force both times, and it's moving up and down same vertical distance. Then the work here is equal to the work here, which means that if this was a positive 50 joules, then the work in section 3 would be negative 50 joules. So the total work would actually be 50 plus 0 minus 50, which means 0. So if you pull up an object up, move it to the side, and put it down, in the end, you actually do a total of 0 joules of work. Now, as far as why it's positive and negative here, that just comes from the fact of in section 1, the force that you apply is vertical and the displacement is vertical. So here it's just going to be FD cosine 0, which just ends up being FD. In section 3, the force you're applying is still vertical, but now it's being displaced downward. If we do FD cosine theta, here the angle is 180, so this would actually be negative FD. So that's why we're getting equal and opposite numbers. If this was 50, this would be negative 50. But why is section 2 0? Well, look at this diagram. When you have an object up, the displacement is horizontal and the force that you're applying is vertical. You're actually lifting it up. You are not applying a force horizontally. There are other forces that are actually contributing to moving it horizontally. Because of this, when we do FT cosine theta, the theta here is 90 degrees and cosine 90 is 0. So this whole thing drops to 0. So that's why in that section we do 0 work. All right. So let's try and use the equation. So pause the video, work self, and we'll go over in a second. Okay. So here we want to find the work being done by the person. So we do FD. I don't really need the cosine theta because I already know that the force that I'm applying is up and the displacement is up. All right. So the next part I have to put in the force. So the force is going to be 20 newtons, and I'm going to multiply that by 3 meters. and I end up getting the work being 60 joules. Now, I know what you might be thinking is, why is the force 20 newtons? There are two key phrases: constant velocity and slowly. So the constant velocity is telling me that the two forces acting on the object is the applied force and the gravitational force. The gravitational force is going to be mass times gravity, which is 20. And because it's constant velocity, I know that these forces have to be balanced, so this also has to be 20. Now, as far as why slowly matters, that basically means that over this 3 meters, the applied force is essentially, on average, 20 newtons. If you want to get technical, if you want to get very specific, there's a brief moment in the very beginning where the person does have to apply a force that's slightly greater than 20. And at the very top, when he stops, he does have to apply a force that's slightly lower than 20 newtons. But in total, on average, the person's applying a net force of 20 newtons, or not a net force, but an applied force of 20 newtons throughout the entire thing. So that's kind of where the slowly comes in. If it happened quickly, then the difference between the force before and after would actually be much bigger. So that's just a key word that they use. Don't overthink it. Here's the next question. Pause the video, work itself. I'm going to go in a second. All right, so for part A, they want to know how much work's being done by the worker. So what I want to do is I want to break this into components, mainly because of the next parts. So I draw my FBD. I have the force of gravity pulling down. I have the normal force pulling up. The applied force, or the tension force, is going up and to the right. So I'm going to break that into an up component and a rightward component. And then there's going to be friction going to the left. I know it doesn't say it here, but it's something that we're going to find out later on. So they want to know the work being done by the worker. Now, the worker is applying these two forces, the force vertical and the force horizontal. The object is moving along a horizontal floor. So the force that I want to actually find is this. So I'm going to do Fx equals F cosine theta, plug in the 69 cosine 30, and I'm getting 59.8 newtons. Now that I have this, I can plug it into the equation Ft. I plug in the numbers 59.8 and 10, and I get 598 joules. Notice that I did not include the cosine theta here, because in this case, now that I broke it up into components, the theta would be 0 degrees. If I wanted to, I could have instead combined both of these into one step and done 69 newtons times the 10 meters, and then times this by cosine of the angle between the force, which the 69 newtons, and the horizontal distance, which would be 30 degrees. You'll notice that it's the same thing. It's just whether I attach it into the work equation or I do it in the force separately. Again, I want to do this for a very specific reason, so that's why I went this route. But it's the same thing regardless, as long as you're making sure that you're paying attention to the angle. Alright, so here's the next question. Pause the video, work itself, and we'll go over in a second. Alright, so now I need to know the work being done by the normal force. Alright, so I know that the force of gravity is 150. I can use the y component, F sine theta, to find that this has to be 34.5. So to find the work being done by the normal force, basically this just means that I have to put in the normal force in for F. So the work done by the normal force is the normal force times the displacement times the angle between those two. So the normal force, if I look at this, I didn't do the work for it, but we can see that in the vertical direction, the forces have to be equal to 0. So Fn plus 34.5 minus 150 equals 0. Move things around, and we end up getting that the normal force has to be 150 minus 34.5. Plug that into 10 meters, and then the angle between the displacement, which again is horizontal, and this vertical normal force is going to be 90 degrees. So displacement is this direction, the normal force is this direction. That's 90 degrees. Plugging that all in, I end up getting 0 joules. And in fact, in a lot of cases, if the object moves horizontally, every vertical force is going to apply 0 joules of work. That is just, natural. All right. All right. So here's the next question. Pause the video, work itself, and we'll go over in a second. All right. Now we want to know the force being done by the work being done by the frictional force. So the equation is Ff equals mu Fn. I'm going to use the normal force, which again was the 150 minus the 34.5. So I get 115.5 times by the coefficient of 0.4. And I get that the frictional force is 46.2 newtons. So when I go to find the work, I'm going to do the force of friction times the displacement times cosine theta. 46.2 newtons times 10. And again, my displacement is to the right horizontally. Friction is to the left horizontally. That is an angle difference of 180 degrees. So I end up getting negative 462 joules. Notice that this angle only affects the sign. It makes it so that the work is now negative. If you want, you could always throw out the cosine theta part and just remember at the very end that this work has to be negative because, well, let's be real, we know friction always takes energy away from objects. So if there's friction going on, it's doing work against the object to slow it down. So that work shouldn't be positive, it should be negative. All right, so here's the next question. Pause the video, work itself, I'm going in a second. All right, so now we have an object on an inclined plane. I'm not going to, I don't have a full-on drawing of the inclined plane, but you have to remember that, we do that whole FBD with the parallel, the perpendicular, the normal force, and the frictional force. So you should know how everything kind of falls in. I'm not going to go into full-on detail with that, but okay, so for part A, there's two different ways that you can find the work being done by gravity. First, as I mentioned, is break up the components. So the gravitational force ends up resulting in two specific components, the FG parallel and an F perpendicular. Now, of these two forces, only one of them actually does work, and it's the force that's going to act parallel to displacement, parallel to the inclined plane, FG parallel. So I could just do FG parallel times the displacement, so 350 sine 37, and then times that by 8 meters, ended up getting 1685 joules. Now, the other way that I could have done is done FG cosine theta. Now here's the thing. You might actually plug the numbers in and you might say, okay, well if I do 350 times 8 times cosine 37, I don't get the same answer. That's because the angle is not 37. The angle that we used in this equation is not the same as this angle. Again, it's a different definition of what the angle is. So this is why I said that you have to be very careful when you're doing these things. So let me try to draw it a little bit better. And that was supposed to be extremely vertically down. Whatever. All right, so my object, my displacement is going along the incline. So it's along this hypotenuse. This is 37 degrees. Theta is the angle between my gravitational force, which is acting vertically downward, and this hypotenuse. This is the theta that I'm using in this equation. So I wouldn't use 37, I would use the complement of 37, since this is a right triangle, and I'd actually use 53 degrees. And now you see that I get the exact same answer. And it kind of makes sense because cosine 53, sine 37, complementary, they get the same number. So that's another way you could do it. Again, this is why I recommend though that you do it this way, because then you don't have to worry about, whether or not are you taking the angle from the vertical, from the horizontal, are you using the angle they give you, are you going to find the complementary, do you have to do some other extra work? You don't have to worry about that. You just do find the force that's acting parallel, times it by displacement, easy enough. All right, part B, finding the work being done by the normal force. Again, I'm not even going to go through the process of finding the normal force because it doesn't matter in this case because it's going to be 0 anyway. Again, it acts perpendicular to the inclined plane, the displacement that it travels. So cosine 90 is 0. All right, here are the last two. So pause the video, work itself. I'm going in a second. Now, to find the work being done by friction, I need to find the frictional force. So it's going to be mu Fn. Remember, for an inclined plane, the normal force is not equal to the force of gravity, but it's going to be equal to the perpendicular component of the gravity, which is Fg cosine theta. So I do the zero point 0.3 times the perpendicular force, and I end up getting about 84 newtons. Then what I can do is use the work equation, force times displacement. I do 83.9 times 8, and end up getting negative 671 joules. Again, you might be wondering, how did I make the force negative? This is just I'm just trying to show other ways that you can go about using these equations and still getting the same idea. If you recall, in the previous parts, I showed how you could either find the force's components, and then you won't have to worry about the cosine theta in the work equation, or you can leave the force pure, if you will, and then take advantage of the cosine theta afterwards. The same idea applies here. If we wanted to, we could keep the force as being a positive number and then do the whole cosine 180, or I could take advantage of the fact that I know that displacement and force are in opposite directions, so the force would end up being negative 83, negative direction, negative value, and then I don't have to worry about the cosine theta. Either way, it's the same idea. Tomato, tomato, potato, potato. So as long as you get the sign there, it doesn't matter how you got to it, as long as it's a reasonable way. And the last part, the total work being done. Since work is a scalar, I could just add up all these numbers that I just found. So I found the work being done by gravity, the normal force, and friction. Plugging these all in, I get 1685 plus 0 minus 671, which gets me a whopping total of 1014 joules. Now, if this was the actual final question, it's reasonable to think, do I have to go through all this work? Do I have to find the work being done by each individual force and then add them all up in order to find the total? Well, just like how in parts A through C, the work being done by each specific force essentially changed the force to whatever they're saying. It turns out that if I wanted to find the total work being done on the object, that means that the force is going to be the total force acting on the object. But if you remember in the dynamics section, the total force acting on an object is just called the net force. So we could have actually saved ourselves a lot of trouble and done the net force on the system, multiply that by 8 meters, and I would have gotten the same answer. Again, it's the same idea. Whether we find the work of each force and then add them up, or I find the force, add them up, and then find the work, I'm still doing the same steps. Whether or not it's in a specific order, it doesn't matter. All right, this is the last thing that I need to talk about with work. And it's essentially, what do we do when we have a force versus distance graph? So if we have force that changes over time. Now you might be inclined to say that I could just do work equals force times distance. So if I have 100, if we're doing the entire 1 meter, you might think that the work is going to be 100 newtons times 1 meter, which gets us 100 joules. However, this is wrong. This is wrong because of the fact that this 100 meters is not acting along the entire 1 meter. It's just the final point. In fact, it only reaches that for a brief moment. Every moment before that 1 meter is a lot less. So this would give us less energy than if we actually applied 100 newtons right from the get-go for the entire 1 meter, as opposed to slowly increasing our force to 100. So we have to remember that when we have a graph, we have two choices. We either do the slope or do an area. You are not really supposed to be plugging numbers into equations. It turns out here that we're going to do area under the graph. This makes sense because if you pay attention, slope is essentially division, and work is and area is multiplication. In that work equation, it's force times distance. That's multiplication. So that means I'm going to take the area. So for the entire, let's say we're doing it for the whole 1 meter, I have a big triangle. The area of a triangle is half base times height. The base being 1, the height being 100. It actually turns out that the work being done is not 100 joules, but 50 joules. So definitely a very big difference between the two. So just keep that in mind, that when you have a graph, always either take the slope or take the area, and pay attention to which one you're doing. That's it. In the next video, we'll talk about potential energy, and we'll do a few practice questions with that. I might actually combine kinetic energy into it, since it might be a little bit easy to combine them. But that's it for work. I know there was a little bit to go over, so just make sure that you go through some practice problems. If you have any questions, feel free to let me know. Otherwise, good luck. Have a great day.